At a 2-unit level, all of these functions that we've been looking at are in terms of time, and so is projectile motion for that matter. But in extension 1 and extension 2, we can look at these equations in terms of the displacement, not just the time. So how does it work? So velocity is some function of the displacement rather than a function of time. Okay? What we can say is this: acceleration, and this is where we've got to be careful, is the derivative of velocity still, but not just velocity by itself, but the derivative of half velocity squared. Right? So when it's with respect to time, we can just differentiate velocity and we get acceleration. But if it's with respect to displacement, then we have to differentiate a half v squared. Okay? Let's prove it. All right, so as I say, we know acceleration is the derivative of velocity with respect to time. Now, I can use our chain rule, implicit differentiation, call it what you will, but I could rewrite dv to t as dv dx times dx to t. Now, dx to t is velocity. So I now have dv dx times velocity. Well, v, I could rewrite. V is the derivative of a half v squared with respect to v. Now the dv's cancel, and we're left with d dx of a half v squared. So this is why we have to differentiate a half v squared rather than just v when it's in terms of displacement. All right, so we've been given an acceleration in terms of displacement. We want to find its velocity in terms of x. They've given us some initial condition. So our thought process, we see the question, oh look, acceleration's in terms of displacement. So acceleration, I know that is the derivative of a half v squared with respect to x. So therefore, integrate both sides, I'll get a half v squared is 3x minus x squared plus a constant. Initial conditions. I know that when velocity is 2, x is 1. So I can work out my constant. In this case, it happens to be 0. So velocity squared is 6x minus 2x squared. But that's velocity squared. We want to find velocity. Velocity is plus or minus the square root of 6x minus 2x squared. Now this is where it's different. Because it's in terms of displacement, we actually can have two answers for velocity. Now, when it was in terms of time, you can't. Because at any particular point in time, you could be only doing one thing. But here, there's no mention of time in here. This would be at two different times. At one time, when I'm at that particular position, I might be moving to the right. But then later, at another time, at that same position, I might be moving left. So it is possible to have both a positive and a negative velocity. Now, another way of setting this out, I personally prefer to use v to v dx rather than d dx of half v squared. If you have a look through our working out there in my proof, one of the middle lines was v to v dx. Now, the reason I prefer that is because I can use definite integrals to go and do this instead. So here's v to v dx. So what I do is separate the variables. Everything with v on one side, everything with x on the other. So if you like, I've multiplied both sides by dx. And then I'm integrating both sides. But I've got to match the limits. Well, I know when x is 1, velocity is 2. And then the top, well, this is the formula that I want to find. What is x when v, or v equals x? And I just go and do these definite integrals. So integrate v, what do you get? Half v squared, which links back to here. So I know I've got half v squared going from 2 to v, but on the right-hand side, I've got 3x minus x squared going from 1 to x. Substitute in, I'll get a half v squared minus 2, and on the right-hand side, I get 3x minus x squared, also minus 2. Move the minus 2 over, multiply both sides by 2, and you can see we get the same thing. V squared is 6x minus 2x squared. The reason I like doing it with a definite integral, I never forget to find the constant, because the working out finds the constant for me straight away. Now in this case, it wouldn't have mattered because the constant turned out to be 0. But that's just lucky more than anything else. Note, what's really cool about this is we can now tell a little bit about our particle, Bob, if you like. Poor old Bob has a very boring life because we know velocity is always positive. Therefore, 6x minus 2x squared is always greater than or equal to 0. If I solve this inequality, I get the answer, x is always in between 0 and 3. So that is Bob's life. And that's all Bob does. It's in between 0 and 3. So it moves between 0 and 3 and nowhere else. All right. Here's another question. Once again, acceleration is in terms of displacement. It is 3x squared. Initially, the particle is 1 unit to the right of the origin and is travelling with a velocity of root 2 meters per second in the negative direction. Find x in terms of t. All right, so we're going to find that original displacement equation in terms of time, even though our acceleration formula has no mention of time whatsoever. I know you're looking and thinking, what sort of crazy maths is this? Is it magic? Yes, it is. It's the magic of calculus. Okay, so d dx of a half v squared, because look, acceleration's in terms of x. So d dx of a half v squared, integrate both sides, x cubed plus a constant. Okay, initial conditions, something that links displacement and velocity. Initially, when t equals 0, although I don't need to use that because I know where to put t, but we know x equals 1, v is negative root 2, we're moving in the negative direction. Oh, constant equals 0. Look, it's not always going to be 0, okay? Just a coincidence. So there's velocity again, ends up being plus or minus. However, now I've got to make a choice. Because we can only perform calculus on functions. And plus or minus the square root of 2x cubed is not a function. So if I want to now say velocity is dx to t, to go and get this formula, I have to make a decision. Am I going to take the positive square root, or am I going to take the negative square root? Big decision to make. Before I get there though, I know I hate to keep you in suspense. But had I used a definite integral for that question, so all right, I would have started off very similar, but now I'll go v to v dx, separate the variables, just like that, separate the variables. So v to v. The initial condition they told me, when x is 1, v is negative root 2, and then we're trying to get a link between x and v. So half v squared on the left-hand side, x cubed, sub in for v, sub in for x, and we get our v squared as 2x cubed. So we get the same equation. So now back to the exciting part. Do we take the positive square root or the negative square root? I am going to take the negative square root. And I know the question on all your lips right now is, exactly. Why? Why? Got to satisfy the conditions that I used to create the formula in the first place. And I used the condition that when x is equal to 1, velocity was negative the square root of 2. So therefore, when I substitute into here, I need to get the answer negative square root of 2. So that's why I had to take the negative square root there. So I would get that answer. All right, now I've got a function, dx to t. Well, let's put it in index form so I can go and integrate. I need to turn that upside down. Now it's with respect to x. So we shall integrate. I now have t as a function of x plus a constant. There must be an initial condition in there that linked time and displacement. And there was. When t equals 0, x was equal to 1. Sub in, Who thought constant was going to be 0? Come on, own up. You know you did. Yeah, see, one honest person. But actually, it's minus the square root of 2. And you think, whew, done that question. No, you have not. The question said, find x as a function of t. It did not say find t as a function of x. We now have to make x the subject. But before I do, keeping in suspense again, had I used a definite integral on this one? So, the t dx, separate the variables. Okay. So I now have integral of the t. I've taken the constant out the front, is the integral of x to the minus 3 on 2. We knew that when x is 1, t was 0. We're trying to find a link between x and t. So integrate. Whenever you get something 0 to t, usually you just write t straight down because you know it's going to end up being t minus 0. Well, that's just t. Sub in the x, sub in the 1, and we have the same answer. So let's make x the subject of the formula. T plus the square root of 2 is the square root of 2 over x. Okay, therefore 2 over x is t plus the square root of 2 squared. Therefore x over 2 is t, and then multiply by the 2, and we have our function. And all we started with, I'll have you remember, all we started with was acceleration was equal to, what was it equal to? 3x. Let's have a look at an HSC one. What's the time? Oh, yep, we've got time, good. Okay, a particle, commonly known as Bob. Bob's moving along the x-axis, position 2 meters to the right, that is x equals 2 when t equals 0. Initial velocity of 5, acceleration given by 2x cubed. What do we notice? Accelerations in terms of displacement. Aha. Show that the velocity is x squared plus 1. Okay, let's do it. Well, d dx of a half v squared. That's acceleration when it's in terms of x. So half v squared, integrate both sides, quarter x4. Got to find the constant. Where's the condition? There it is. X equals 2, v equals 5. Substitute in. Constant's a half. Sub back in. And I've also multiplied both sides by 2 there as well. So v squared is x to the 4 plus 2x squared plus 1. Hang on. That's a perfect square. But before we go there, had I chosen to do it as a definite integral, then I would have gone, v to v dx is 2x cubed plus 2x. You know what we're going to do now? What are we going to do? Separate the variables. Woo, there we go. So v to v. But we know when x equals 2, v equals 5. So we want to link between x and v. All right, let's integrate. Notice what I did here this time, because I knew I was going to end up with a half v squared. So I just multiplied the other side by 2 straight away there. Okay. Sub in the v, sub in the x and the 5 and the 2. There's v squared as the subject. But as I was saying, go back to it, we looked at it and went, oh my gosh, that's a perfect square. So v squared is x squared plus 1 squared. Therefore, v is x squared plus 1. Are you happy with that? Yes. The correct answer was no. Because it should have been v is plus or minus x squared plus 1. Why did I choose the positive? Right. So I need to add in. Hang on. I know velocity is greater than 0 in order to satisfy the initial conditions. Hence, let's go find that expression even for x in terms of t. Well, dx to t is x squared plus 1. Integrate. I've gone straight to the definite integral this time because it's fun. So, link them together. We know when t equals 0, x equals 2. So that gives me t equals, inverse tan. Inverse tan. So t is the inverse tan of x minus the inverse tan of 2. Unfortunately, that is t as a function of x. They want x as a function of t. So inverse tan x is t plus the inverse tan of 2. So x is the tan of t plus inverse tan of 2. And that's how mere mortals would leave the question. But we know tan plus tan on 1 minus tan tan. Hey. So, X is tan t plus 2 and 1 minus 2 tan t. Far more impressive. Alrighty.